Difference between engineering and true stress-strain curve. The stress-strain curve is obtained from the tensile test. It represents the mechanical behavior of the material under tensile loading. So based on that, there are two ways to represent this curve. The first one is the engineering stress-strain curve, and next would be true stress-strain curve. So now, to understand the both engineering and true stress-strain curve, we must first understand how the stress and strain curve is obtained. So, as we seen in the slide, the stress and curve is obtained when the tensile test. We are going to have a short note about the tensile test. So, for what the tensile test is used, it means it is a mechanical test used to determine the behavior of the material under the uniaxial tensile load. The uniaxial tensile loading, it means the force applied to the specimen along the single axis. So, taking your specimen, so in tensile testing, the specimen is clamped in a universal testing machine, and the uniaxial tensile load is applied gradually. So, as the load increases, the specimen elongates, and we measure the elongation. So, from the load and elongation data, stress and strain are plotted and calculated. So, from this, the stress and strain can be calculated. So, when the load is initially applied to the specimen, the material behaves elastically. After that, the yield point is there. After the yield point, the plastic deformation begins. So, during the plastic deformation, necking occurs where the cross-sectional area reduces. So, due to the reduction in the cross-sectional area, the specimen experiences a fracture at a point. As in this test, the stress-strain curve in this shows the elastic region, plastic region, necking, and finally the fracture takes place in the specimen. So now we understood how the tensile test is being performed. So let's see the stress and strain are actually how they are calculated. So first we look on into the engineering stress and engineering strain. The engineering stress is defined as the applied load by the original cross-section area. So it is represented as sigma is equal to F by A naught. F is the applied load and A naught is the cross-sectional area. Then engineering strain, it is defined as change in length by original length. So epsilon into del L by L naught. So in engineering stress strain curve, the original dimensions are used throughout the experiment. Now we can observe the behavior of the engineering stress strain curve. In engineering stress strain curve behavior, the curve increases linearly in the elastic region. The photograph in that, the red would be the engineering stress strain relationship, in that the curve is linearly increases in the elastic region, and after yielding the plastic deformation occurs. So at the plastic deformation, the necking occurs. So in plastic deformation, it reaches the ultimate tensile strength. At that point, the necking begins and the engineering stress decreases after the point because it uses the original area. The linear elastic is followed by the yielding and plastic deformation occurs up to the UTS, and then the stress decreases after the necking, and finally the fracture is experienced by the specimen. So in engineering stress strain curve, the original cross-sectional area has been used. So however, in reality, the cross-sectional area keeps changing during the deformation. So to account this change in actual dimension, the concept of true stress and strain is being used. Let's see what is the true stress and strain. So true stress is calculated using the instantaneous area. So 2 stress sigma T equal to F by A. Here the area is instantaneous cross-sectional area. The two strain consider continuous change in length. So here the dimensions at every instant are considered. So it represents the actual deformation behavior. So now let's see the two stress strain curve behavior. In two stress strain curve behavior, the elastic region coincides with the engineering curve. As we see the picture, here the blue is the two stress strain and the red is the engineering. The elastic region of the both the stress strain curve are more or less same. So it coincides at a point. Then the difference increases in plastic region. Here, after the yield point, the two stress strain curve, the stress being increased. After in the engineering stress strain, in plastic deformation, after necking, the stress being reduced. It is due to the original area has been used in the engineering stress strain curve. So here the same thing are given. The stress continues increasing after necking, and it has a continuous increase in after necking is due to the instantaneous area. So it is more accurate representation of the material behavior than the engineering stress strain curve. So let's have a small comparison about the engineering stress and true stress. So in engineering stress, it uses the original area. In true stress, it uses the instantaneous area. So next difference would be the stress decreases after the UTS. During plastic deformation, necking occurs. After the necking, the stress being decreased in the engineering stress. The same way, after the necking, in the true stress is being increased. It is a major due to the original area and instantaneous area. In engineering stress, the original area has been considered. So after the necking, reaching the ultimate tensile test, the stress being rapidly decreased. In true stress strain, the stress is continuously increasing due to the instantaneous area. So in engineering stress strain, nominal stress is being used. In true stress, is actual stress is used. So engineering stress is more the common application. It is mostly used in the structural designs. In true stress, it is used in the metal forming operations. So now let's see the relationship between the engineering and true. These equations are the mathematical relationship between engineering and true values. So sigma t is equal to sigma 1 plus epsilon. Epsilon t is equal to ln of 1 plus epsilon. Here the difference significant is large plastic deformation. Here the difference becomes more significant at the large plastic deformations. Next, the applications in the structural designs. So the two curves are majorly used in metal forming operations like rolling, forging and extrusion. It is due to the deformation large. So two stress strain curve is preferred in metal forming operations because the deformation is large. The true curve is more important for the plastic deformation analysis. So from based on the differentials application, we can conclude that engineering stress strain curve is simple and based on the original dimensions, and the true stress strain gives the accurate representation during plastic deformation. Both are dependent on application. Both the engineering stress strain curve and true stress strain curve are important depending on their applications. Thank you.